What exactly is linear motion? I've showed it to you before. In a previous video, I showed you this awesome animation. If you send a box scooting along in a horizontal direction, that's linear motion. Here's another example. If you drop an object and it falls straight down, that's linear motion. If you were to drive along this road, that would be linear motion. You could also call linear motion one-dimensional motion. Hopefully you remember this guy, Galileo Galilei. Back in the 1600s, he was the first to challenge the ideas of motion. Back in the 1600s, he was the first to challenge the explanation of motion that had held for almost 2,000 years. He decided that an object will keep moving unless a force brings it to a stop. This is commonly referred to as the law of inertia, where inertia is an object's resistance to change in motion. Galileo also introduced the concept of speed. He defined speed as distance over time. So the question I have for you, is this still how we use the term speed today? Do me a favor and actually see if you can answer that. Well, many people I know would say yes, this is how we use the term speed. But to me, the answer is actually no. I'll give you some examples that will hopefully demonstrate why that is. Here is my house, and here is SUU where I work. Every day I drive from my house to SUU, and when I do, the path looks something like this. Several times as I've been driving, I've been careful to track the total distance that I travel, which was about 10 miles, and the total time, which is about 20 minutes. For reasons that'll be made clear in a moment, I'm also defining 20 minutes as 1/3 of an hour. If speed is distance over time, then my speed is right here. If I do some algebra on that, I end up with 30 miles per hour, where, just to be clear, MPH means miles divided by hour. Well, that's fine and all, but one day I was driving to work, and I was being very careful to follow the exact same pattern as all the times before. I was expecting a total time of 20 minutes on my trip. And I'm driving down a road when I have to come to a stop because I've been pulled over. The police officer states that I was going 45 miles per hour in a 30 and wants to give me a ticket. I explained to the officer that speed is distance over time, and I was clearly going 30 miles per hour, so I don't deserve a ticket. The officer, of course, is unimpressed and gives me the ticket anyway. I'm happy to say that this didn't actually happen, but I'm hoping it'll prove a point. Clearly, not everybody agrees that speed equals distance over time. Remember that the definition from Galileo was given over 400 years ago. We've certainly increased our understanding of motion since then. Nowadays, we have different types of speed. We're going to consider just two for now: instantaneous speed and average speed. So when the officer stated I was going 45 miles per hour, that was my instantaneous speed. As I'm driving in my car and I'm watching my speedometer, which speed is that? Do me a favor, think about that question and answer it for yourself. I'm sure you know from personal experience that when you're driving, your speedometer is constantly going back and forth, so that would clearly be instantaneous speed. So what is the speed that we calculated of 30 miles per hour? that would be the average speed. If we wanted to understand instantaneous speed in further detail, we're going to need to bring in calculus. That's clearly beyond the intentions of our course, so we're not going to go too far into instantaneous speed. Average speed, however, we can define as simply the total distance traveled divided by the time it took to travel that distance. So what can we do with the average speed? As I play with this formula, I'm going to simplify it down a little bit. I'm going to use d for distance, t for time. V will represent speed, but I want to keep average in there to indicate it's not another version of speed. This definition is useful for other things if we do a little bit of algebra. Because this is an equality, I can do anything I want as long as I do the same thing to both sides. I'm going to multiply this side by time, and then I'm going to multiply this side by time. The reason why I did that is because the times now cancel out. Now I have a useful relationship for distance, so I'm going to rewrite that a different way. Another thing I could do is I'm going to multiply both sides by time again. However, I'm also going to divide both sides by average speed. That way this cancels out, and now I have a definition of time as well. Let's see how those are useful. In this example, I'm going to look at distance. How far does a car travel in 30 minutes if it has a constant speed of 42 miles per hour? Well, I have a speed in the problem and I have a time, so I should be good. There is one issue here though. Notice that the problem said constant speed, but my equation above says average speed. So before I go on, I should answer the question of, are those the same thing? If your speed is not changing, then there's no deviation in the speed to change the average value. Therefore, when you have a constant speed, that is just the same as your average speed. Also, if your speed is constant, then at any given moment, your speed is the same as any other given moment, so you can say that your instantaneous speed is also the same as your constant speed, which is the same as your average speed. So we've decided that average speed and constant speed are the same thing, so we'll go ahead and apply this relationship. So for me to find distance, I just simply use my result of average speed and time. I'll plug in those values. Now notice here, I am using 1/2 hour for 30 minutes. The reason why I want to do that is because now my hours cancel out and I'm just left with miles. If I had just plugged in 30 minutes, that's not technically wrong, but my time wouldn't have canceled out and I wouldn't have been left with miles. And our answer is 22 miles. We're going to change gears just a little bit here. I'm going to start with a question, and I want you to really think about this. So I'm going to pause for at least 30 seconds. Please read through this and come up with your own answer. When I ask this question in class, I get a lot of A as an answer. Now it does seem familiar, but unfortunately that is incorrect. The best answer for this question is E, none of the above. So we need to define what velocity actually is. Velocity is a quantity that describes both the speed of an object and the direction it is moving. The key to this definition are these two words, speed and direction. Velocity requires both of those. That makes velocity a vector. If you remember from our previous video, a vector is any quantity that must consider how much and in what direction. Velocity is a vector because the direction is just as important as the speed or the how much. So with our new definition of velocity here, let's go over an example. The car was traveling north at 50 miles per hour. This is an accurate description of velocity. Notice that you have direction and speed. I don't know if you caught it, but the animation for my text as it zoomed upwards was also a demonstration of velocity because it had a speed and a specific direction up in this case. Earlier we talked about constant speed, so now let's talk about constant velocity. Like so many times before, let's answer this question with another question. We're going to assume for this example that the Earth goes around the Sun in a perfect circle with a constant speed. In real life it's not exactly that, but it's actually pretty close, so this isn't a bad example. So if we make those assumptions, my question is, does Earth have a constant velocity? Please take at least 10 seconds and really think about this. To address this question, I want to point out that at one moment the Earth is going in that direction, and then at a later time it's going in that direction. So the direction is clearly changing. Direction is a part of velocity, so if the direction is changing, then the velocity must also be changing. So the answer is definitely no. Even though it has a constant speed in our example, it does not have constant velocity. So let's go ahead and give a specific definition for constant velocity. It's when an object moves with a constant speed and in a constant direction. So here's another question. If an object moves with constant direction, what will be the shape of its travel path? There's only one option in this case. It's got to be a straight line. I should mention that a straight line path is also called linear motion or one-dimensional motion. I want to also point out that a straight line doesn't have to be a horizontal line. In this case, my motion is diagonal, but it's still following a straight line, so its direction is still constant. I've modified our earlier definition just a bit to say that constant velocity is when an object moves with a constant speed and in a straight line. If an object changes direction in any way, it does not have constant velocity. Here's another type of velocity that I want to consider. It's known as relative velocity. And for this one, again, I'm not going to give you a formal definition. We're going to go through some examples, and I think it should make pretty good sense. Imagine this person is jogging along at 6 miles per hour. We're going to track their initial position, and at some later point, we're going to mark a final position. Notice that this is linear motion. Earlier we defined speed as distance over time, but speed can also be defined as a change in position divided by time. Notice that a change in position is a distance. I also want to point out that this 6 miles per hour in the right direction is a velocity, because we have direction and speed, but this velocity is specifically relative to the ground. Now imagine that on the ground I've added a moving walkway. Think of the ones that you see in airports. This walkway is moving at 3 miles per hour in the left direction. We're going to repeat this situation with the jogger moving at 6 miles per hour, but they're going to be running on the walkway. So before I show you, I need to emphasize that in this case, the 6 miles per hour is now relative to the walkway because that's the surface they're running on. So what would that look like with the walkway moving to the left at 3 miles per hour and the jogger running to the right at 6 miles per hour? I specifically want to know, if this was you, what is your speed relative to the ground? Let's watch. Yeah, I don't know if you noticed, but you're definitely moving slower. To help emphasize how much slower, this time I'm going to send out a ghost image of when the person was running at 6 miles per hour relative to the ground, so you can see the comparison. If you noticed, when the ghost image reached the final position, you were exactly halfway in between your initial and final position. That would imply that you were going exactly half of the speed you had originally, or 3 miles per hour. So how we figure that out mathematically is we keep in mind that these are vectors. So here I have 6 miles per hour to the right and 3 miles per hour to the left. I'm going to treat right as positive and left as negative, and my total velocity is just the sum of those. So the right would be positive 6 miles per hour, and then I'm going to add to it the negative 3 miles per hour, negative implying the left direction. The total is obviously 3 miles per hour, and the positive indicates you're still moving to the right, which is the half that we expected. Let's mix things up a little bit. This time we're going to have the walkway going in the same speed, but now in the same direction as you. So in this case, what is your speed relative to the ground? You can probably guess in this case, you're definitely going faster. To see how much faster, I'm going to try that again with the ghost image. And the ghost image is the person running 6 miles per hour relative to the ground. If you didn't catch that, when you reached your final position, the ghost runner was 2/3 of the way across. So if we do our vector calculation, this time I'm still adding vectors, but now both of them are positive. So I'm left with positive 9 miles per hour. So you can see in this specific example, I increased my speed by 50%. Let's go through just a couple more examples. So what if we have two objects going in opposite directions at the same speed? For this example, why don't you imagine that these are cars? I want to know, what is their speed relative to each other? Let's see. Your intuition is probably good enough on this one. They would be going 60 miles per hour relative to each other. This is an example of why head-on collisions are typically the worst in terms of damage. Let's do a second example. In this case, they're going in the same direction, but in different speeds. And the rear one is going faster, so it has the opportunity to catch up to the front one. And what I want to know is, what is the speed of the orange box relative to the blue? If you could tell, relative to each other, their speed seemed a lot slower than the 60 mile per hour orange box. And your intuition, again, is probably good enough. It was 30 miles per hour. So in this case, it would be like a rear end collision, which typically isn't as damaging. However, think about it, 30 miles per hour for heavy vehicles can still cause a lot of damage and can still be dangerous. In our last example, imagine you're driving a car at 25 miles per hour. Your passenger is your friend, and they throw a snowball straight forward from the car at a speed of 20 miles per hour. So what I want to know is, how fast is the snowball going relative to a person standing on the street? I want to mention first that I'm going to assume that the car turned before it hit the person, because if it didn't, I'm sure the person wouldn't care much about the snowball for long. So your intuition should tell you 45 miles per hour. If you've ever been hit by a snowball, 25 miles per hour is uncomfortable, but 45 miles per hour is much worse. I wanted to give you this question because I occasionally see people doing stuff like this, throwing stuff out of moving vehicles, and I always wonder, do they really understand the effect that their car's speed has on the object they're throwing? It can really cause a lot of damage if you're not careful. In this video, we discuss speed, and then we turn that into velocity, and then we discuss constant velocity and ended with relative velocity. So you're probably wondering, are there any other types of velocity that I should be concerned about? And the answer is, of course, yes. Yes, there is. Let's define one more: changing velocity. This is simply when speed or direction or both change. My last question for you is, what is the special name we give to changing velocity? Please think about that and see if you can answer that. What is the name for changing velocity? Well, I hope you knew that it was this. A change in velocity is called acceleration. Acceleration is what we're going to discuss in the next video.